Right, so I've found this nice Casio emulator, an 85 version, scientific. Since 9.3 is pretty much the same as 9.2, I thought I'd get this emulator and we could code in the numbers there so you can see them and not really bother writing out the equations. So we've got our equations there from the tutorial sheet. So let's go through the calcs we need to do. So part A, principal plane, we're going to be using this equation here, number 1. Have a look at your equation of state. Get it so that it's everything, all the arrows are pointing in the way you want them to point them. So our shear is a negative shearing effect. Everything else is fine. So it's easy to put in negative numbers into here. So we're going to first find out what 2 theta pi is. Okay. So is this going to work? Actually, can I use this? First tan. So I've got -2 times 15 divided by 10, take away 50. Close bracket, close bracket. Gives me probably the wrong answer. Okay, 36.686. Well, should have rounded up, make that 7. So principal plane 1 will be 18.435 degrees, and because it's inverse tan, we want to add on another 180, but that's divided by 2, so we want to add on 90. And so the other plane will be at 108 degrees, 0.435 degrees. Okay, so that's A. Principal stresses. So we're going to use this equation here. So what am I going to do? I'm going to say 10 plus 50 divided by 2. So the first one we'll do is the minimum. Take away square root. And 10. Open another bracket. Take away 50. Close the bracket. Divide it by 2. Close that bracket and square it. Plus, I'm not going to bother with the negative because when I square a negative, it should be a positive. So I'm going to find that. Ooh, nice number, isn't it? So that gives me the minimum of 5 megapascals. And then do the replay button. Where's delete? And replace that with a plus. "55 megapascals." So that's part B. And since it's asking for shear stress here, I assume it doesn't want the shear stress for part B. Part C, the orientation planes for the shear stress. So that's using equation 3. So we're going to use inverse tan again. Right, negative, open the bracket. We've got 10. Take away 50. Divided by 2 times minus 15. Let your calculator work out all the negative signs and whatnot. So that then gives me 2 shear and stress will be minus 53.13. So the first shear and angle, I probably only want the first, divided by 2, is minus 26.565. Degrees. Okay, what's the part D is the maximum thing. So we want to find this thing here. Eh. So what I'm going to do is I'm going to use equation 2. So I'll take the maximum and then I'll take away the minimum. And what you can see is that then those two terms will cancel out, and then we're going to get this, take away this again, which would be positive. So we're going to get this term, or 2 of them terms, so we divide it by 2. So I don't have to work out that. And that's then going to be 50, take away 5, divided by 2, I don't need my calculator, 25. And then part E, so that's asking me if I take this to be my principal shearing. So what have we got? So that's going to be pointing down here. What's the normal stress going down in this direction? So to get there, to go from here to here is being 26.565 degrees. So I want to use this equation. Note that these equations are for rotating anti-clockwise. So the value here I'm going to put in is going to be a negative because I want to rotate from here down to here. So I want to rotate in a clockwise sense. So what numbers are we using there then? So the first one will be open bracket 10 plus 50 divided by 2. That's the first bit. And then we've got plus, open bracket, 10, take away 50, divided by 2. And then we will times that by cos. So we are swinging this way, so it's a negative. So minus 2 times 26.565, close the bracket, and then plus, actually it's minus, because it's minus 15, times by sine, open the bracket, and then we've got another minus 2 times 26.565. Close the bracket. And that's my, oh, and there we go, nice number 30. So the normal stress acting along the shear is going to be 30 megapascals. Okay, that's cool. Looks up also.